All right, let's dive right into this explainer. Today, we're bridging the gap between abstract calculus and real world physical motion. If you've ever looked at physics equations and thought, man, this is literally a foreign language, well, you're definitely in the right place. We're going to take the messy, chaotic movement of the real world and translate it into the clean, structured dialects of math and graphing. Let's get into it. So think back to your very first physics classes. You were probably handed these perfectly pristine, kind of unrealistic scenarios, right? Assume a frictionless vacuum, or hey, just ignore air resistance. But let's be real for a second. In the actual world, gravity actually fades the higher up you go, and air absolutely pushes back against moving objects. So how do we handle that? How do we calculate unpredictable scenarios when the basic rules are constantly shifting right beneath our feet? Here's our roadmap for today. 1. Complex real-world motion. 2. The core physics graphs. 3. Calculating from curves. 4. Advanced graph analysis. 5. Spotting impossible physics. And finally, 6. Expanding into 3D motion. Starting off with Section 1. Complex real-world motion, the dialect of calculus. Okay, here's a real-world puzzle for you. Imagine a ball falling from a tower, but this time we're not in a vacuum. What actually happens when air resistance isn't ignored? What if the air pushing back on the ball is perfectly equal to the ball's momentum? As the ball speeds up, that resistance gets stronger. The acceleration is constantly changing. Standard high school formulas? Yeah, they just won't cut it here. Because our acceleration is constantly changing, which we can write as a equals 10 minus v, we can't just plug in a single static number. Instead, we have to set up an integral. By integrating that changing acceleration over time, we unlock the exact velocity equation for this messy reality. Just look at that elegant equation we get. V equals 10 times 1 minus e to the negative t. See that e to the negative t part? That simply means that over time, the velocity naturally levels out to a constant top speed. Pretty cool, right? Let's look at another fascinating scenario. Imagine a hypothetical planet where gravity isn't just a constant 9.8 or 10 meters per second squared. Instead, it linearly fades away as you climb higher in altitude, eventually hitting zero at exactly 1,000 meters. If you wanted to shoot a ball up so it completely escapes this gravity field, you'd have to account for gravity weakening every single centimeter it travels. By defining gravity as a linear function of height, let's call it y, we once again use the dialect of calculus. We integrate to find the precise initial speed required. Honestly, calculus is like a universal translator. It takes a constantly shifting environment and turns it into a solvable equation. Moving on to Section 2, the core physics graphs, the dialect of visualization. If you ever get lost in kinematics, think of this as your ultimate graphing cheat sheet. We're looking at 3 main graph types: position time, velocity time, and acceleration time. Now, in the language of graphs, the slope is our derivative. It tells us the rate of change. On the flip side, the area under the curve is our integral. It tells us what has physically accumulated. So taking the slope of position gives you velocity, and finding the area under velocity gives you your actual change in position. The absolutely crucial point here is comparing these 2 standard curves side by side to visually prove this relationship. Take a look at the red line on the position time graph on the left. Right where that position curve peaks and goes perfectly flat, the slope there is 0. Now, if you trace that exact moment over to the velocity time graph on the right, you'll see the velocity is sitting exactly at 0 on the y-axis. The slope of a position graph physically translates into the actual value of the velocity graph. And similarly, the steepness or the slope of that velocity graph tells us our exact acceleration. All right, Section 3. Calculating from curves. Displacement versus distance. Take a look at this velocity time graph. We've got a large triangle sitting above the x-axis and a smaller triangle dipping below it. Remember, the area under the curve isn't just some abstract mathematical integral. It is the literal physical accumulation of movement over time. By calculating the basic geometry, literally just the area of those triangles, we are actually calculating the displacement. That top area, that's positive displacement, meaning moving forward. The bottom area is negative displacement, meaning moving backward. Which brings us to a really vital distinction. Displacement is your net area. You add the positive space and subtract the negative space to find out exactly how far you are from where you started. But distance traveled, that is the absolute area. The universe doesn't care if you walk backwards or forwards. Your legs still did the work. So for total distance, we force all those negative areas to be positive and just add them all up. It's a subtle graphical rule, sure, but it makes a massive physical difference.
Next up, Section 4, Advanced Graph Analysis, Finding Acceleration from Position.
So, normally, we find acceleration from the slope of a velocity time graph. But what if we have velocity on the y-axis and position on the x-axis? How do we find acceleration then? Well, we use the chain rule. Acceleration equals velocity multiplied by the derivative of velocity with respect to position. Visually, what that means is we take the actual velocity value at a specific point and multiply it by the physical slope of the line at that exact same point. It is such a clever way to extract time-based acceleration when time isn't even on the graph. Now, what happens if we square the velocity axis? If you look at a v-squared versus position graph, the math just untangles beautifully. Because of how the kinematic equations are structured, the slope of this particular line is actually equal to twice the acceleration. So if you can find the slope of this line, simply cut it in half, and boom, you instantly have your constant acceleration. It's kind of like a secret shortcut hidden right there in the geometry. Let's move to Section 5, Spotting Impossible Physics, when math breaks reality. Okay, I want you to put your detective hat on for a second. Mathematics allows us to draw any line or curve we want on a piece of paper. But just because you can draw it, does that mean it can actually happen in the physical universe? Let's see if you can spot where the math totally betrays reality. Here are 4 velocity time graphs. At first glance, they might just look like normal, everyday geometry problems. But every single one of these graphs represents a physically impossible scenario. See if you can spot the impossible situations before I reveal them. Hint: look very closely at the straight vertical lines and pay special attention to that strange loop over on the far right. Did you catch them? All right, here are the physical violations. First, a perfectly vertical line on a velocity time graph implies that velocity changed instantly in 0 time. That requires infinite acceleration, which is, well, impossible. Second, that loop on the far right actually bends backward along the time axis. That means the object is literally time traveling into the past. And lastly, anywhere a curve doubles back over itself vertically, that implies an object has 2 different velocities at the exact same moment in time. The math is super easy to draw, but the universe firmly rejects it. And our final stop, Section 6, Expanding into 3D Motion, the dialect of space. Up to this point, we've essentially been calculating motion on a tightrope, just moving back and forth in one dimension. But visualizing motion in a real-world cricket stadium anchors the reality of 3D space perfectly. And the amazing secret to 3D kinematics? It's not some new, overwhelmingly difficult topic, not at all. It is literally just a copy-paste of the exact same 1D rules we just learned, applied to 3 mutually perpendicular axes, x, y, and z. Here's the simple 3-step procedure to conquer complex spatial motion. First, you divide the movement into those mutually perpendicular x, y, and z axes. Second, you treat them like completely separate universes. Apply your 1D kinematics and calculus to each axis completely independently. The motion in the x direction has absolutely no impact on the gravity in the y direction. Finally, once you have your answers for each, you recombine them using vector notation to get the full 3D picture. Looking at this, the familiar calculus equations for velocity and acceleration simply expand. We use I, j, and k hats to keep our x, y, and z map perfectly organized. But notice, the underlying logic hasn't changed one bit from our very first concept. We're still taking derivatives to find velocity and acceleration. We're just doing it 3 times in parallel to map the real 3-dimensional space. And that brings us to the end of our translation journey. We've taken the messy reality of air resistance and gravity, structured it with calculus, visualized it through slopes and areas, and expanded it into the 3D space we actually live in. If motion is simply a language that can be so elegantly decoded, what other hidden rules of the universe are you ready to translate next? Thanks for joining me on this explainer, and keep questioning the physics around you.